So let's do another example where we apply the definition of a Laplace transform. Suppose we want to find the Laplace of the sine of 2t. This one's going to require some Calc 2 techniques. So hopefully this will bring back some good memories of the fun things you did in there. So if we integrate this one, we're going from 0 to infinity, is e to the negative st sine of 2t dt. Now the trick to this is doing by parts, and we're going to end up having to do by parts twice. So we're going to let u be that exponential piece. So du would be negative s e to the negative st. If we choose u to be e to the negative st, then dv is what's left over, which is sine of 2t dt. We just have to figure out what v is. So let's do integration by parts for that. Not integration by parts, sorry, u substitution. I'm going to do that over to the side. So if we integrate this, u would be 2t. We're missing a 2. And we can compensate with a 1/2. So this would give us 1/2 times the negative cosine of 2t. So there's our v. So here's what we have. We are trying to integrate e to the negative st sine of 2t dt. And that's going to be uv minus the integral of v du. So du, we need that dt there. Now, I'm going to clean that up before I go any further. So a negative times a negative times a negative is still a negative. And then 1/2 times s would be s over 2. So there's where we stand right now. Now we're going to do by parts again because we're going to need it to integrate this piece. And we're going to choose that exponential piece to be u again. You want to choose the same thing for u on both by parts. Anytime you integrate an exponential times sine or cosine, this process will work to help you integrate that. It requires by parts twice. So that leaves dv to be cosine of 2t. So then we need to integrate that cosine. So I'm going to do that off to the side. If we integrate cosine of 2t, we're doing a u substitution. We're missing the 2, and we can compensate with a 1/2. Integrating cosine gives us sine. So our v is 1/2 sine of 2t. So then here's what we have. And I'm writing this complete sentence so you can see what's going on. We started with integrating 0 to infinity e to the negative st sine of 2t dt. And when we did that, we ended up with that negative 1/2 e to the negative st cosine of 2t minus s over 2. And then we had to do by parts for this piece. So here's our by parts. And if we put that together, it's going to be uv minus the integral of v du. Now let's simplify everything in here. And I'm just going to deal with that right-hand side right now. So we have a negative times a negative, which will make this a positive. And then s times 1/2 is s over 2. So you can kind of see what's happening in here. The left-hand side, I have the integral of e to the negative st sine of 2t dt. I also have that on the right-hand side. Now let's distribute that negative s over 2 to everything. So we're going to have a minus s over 4 e to the negative st sine of 2t. And then if I distribute this to this, that will give us a minus s squared over 4 times that integral. Now, notice we have that integral of e to the negative st sine of 2t dt on the left. We also have it on the right. Let's put them together. So what we want to do is add this guy to the other side. So remember, there's a 1 in front of this. So I have one of these over here, and I'm adding s squared over 4 to the left. So 1 plus s squared over 4 would give us 4 plus s squared over 4. So now we have, that's a little side piece. Now we have 4 plus s squared over 4 times that integral. And that's going to be equal to negative 1/2 e to the negative st cosine of 2t minus s over 4 e to the negative st sine of 2t. So you can see how the trick is integration by parts twice. And the reason we do that is because we know if we're integrating an exponential times a sine or a cosine, we'll eventually, after doing by parts twice, get back to something that's the same. We will have the exponential times that sine on both pieces. So then we can move those to the same side. And then now, to get this guy by itself, we can multiply by the reciprocal. So let's do that. So that's your trick to integrating something like this. So if we integrate by the, if we multiply by the reciprocal, then that's just going to give us a 1, which means we're going to have this integral by itself. If we multiply this by that negative 1/2, we're going to be left with negative 2 over 4 plus s squared times e to the negative st cosine of 2t. And then if we multiply this by that negative s over 4, the 4's are going to cancel. So we're going to have a minus s over 4 plus s squared e to the negative st sine of 2t. Now, we still need to evaluate this from 0 to infinity. So if we wanted to write this out formally, we could do that limit as b goes to infinity. I'm going to do this really informally. And keep in mind, this is going in for t because we integrated with respect to t. So if we were to substitute in, before I do that, I'm going to rewrite this. And I'm going to bring that exponential term to the denominator because I think it's going to make it easier to see what's going on. So we're going from 0 to infinity. So let's apply that fundamental theorem of calculus. So we have negative 2. This is going to be cosine infinity. 2 times something that's big is going to be something that's big. Over 4 plus s squared. And then if we have s times something that's big, well, that guy's just getting bigger and bigger. Minus s over 4 plus s squared. Same concept here. That exponent on e is getting larger and larger. And this is going to be sine of 2 times something big is still going to be something big. Minus. This is negative 2 cosine of 0 over 4 plus s squared times e to the 0 minus s sine of 0 over 4 plus s squared e to the 0. Now I want you to think about what's happening here. Sine of 0 is 0, so that piece is gone. That's the easy piece. Think about what's happening over here. Our cosine function is always bounded between negative 1 and 1. So the largest the cosine of anything would be 1, and the smallest would be negative 1. So that's putting a restriction on this numerator here. If we take the cosine of something and we get a negative 1, then the biggest that numerator is going to be 2. Because we would have a negative 2 times a negative 1, which would be a positive 2. And then if we take the cosine of something and we get a 1, then we would end up with a negative 2 in the top. So we would end up with anything between negative 2 and 2 in the numerator. So that's what's going on there as our value changes here that we're taking the cosine of. But in the denominator, it's a different story. Because we have an exponential that's getting larger and larger and larger. So while that top is kind of trapped between negative 2 and positive 2, that denominator is growing without bound. So since that denominator is getting bigger and bigger, and the top is trapped between two numbers, and it's hitting everything between those two numbers, then this guy has to be going to 0. We could use that same kind of approach right here. So if we were to look at this one, we know sine is bounded between negative 1 and 1. So any number we take the sine of, we're always going to get something between negative 1 and 1. We're treating s as a constant here. So this top is always stuck between, two numbers, a positive s and a negative s. But that denominator is getting bigger and bigger and bigger and bigger, which means that whole fraction is shrinking down to 0. So this guy's going to 0. This guy's going to 0. This piece, if we were to simplify, we would have negative 2, because cosine of 0 is 1, over 4 plus s squared, times 1. And then we would have a 0 for that second term. So this piece is heading to 2 over 4 plus s squared. Now, if you think about what is forcing this thing to converge, what's forcing this thing to converge is what's going on with s in that denominator. So as long as s is greater than 0, then that denominator is going to be increasing without bound. So we would say the Laplace of the sine of 2t would be equal to 2 over 4 plus s squared. Now, I think you'll agree that this is a pretty tedious process. There's got to be an easier way. And luckily for us, there is an easier way. There's a table of Laplace values that we can use to help us with this. But before I introduce you to that table, I want to talk a little bit more about some of the properties. The Laplace is actually a linear transformation. So if you think back, if you've taken linear algebra, when you talk about linear transformations, there are two properties that have to hold. There's a scalar multiple property, and then there's a sum property. Well, we can see those coming out here. If we integrate from 0 to infinity of e to the negative st times alpha times some function plus beta times some function, because of the way integration works, we could split this up into two different integrals. Let's distribute so you can see that. So this would be alpha e to the negative st f of t dt. Let me distribute first. And then we could split this up to two integrals. That's using some of the properties that you talked about in Calc 1. And then since alpha and beta are scalars, we could pull those out, and that would get us to this guy. So then what this is saying that is that if we were to take the Laplace of alpha ft plus beta gt, then that's the same thing as taking the alpha times the Laplace of f of t plus beta times the Laplace of g of t. So then as long as we know what this guy is and this guy is, then we'll know what the Laplace of that sum is. So let's look at a few examples. Let's say we want to take the Laplace of 1 plus 5t. So that's the same thing as taking the Laplace of 1, which we've already found, plus the Laplace of 5t, which we've already found. And that's the same thing as taking the Laplace of 1 plus 5 times the Laplace of t. So instead of having to do the integration for this guy, if we already know this and we know this, then we know that. So then we're going to have the Laplace of 1 was 1 over s. The Laplace of t was 1 over s squared. So our final answer would be 1 over s plus 5 over s squared. Or we could say s plus 5 over s squared. Now that restriction on s, you have to think about the intersection. In this guy, when we found the Laplace of 1, s had to be greater than 0. I'm going to write this over here. When we found the Laplace of t, s had to be greater than 0. So this works when s is greater than 0. Let's do an example that's going to combine some other ones. Let's say we want to take the Laplace of 4 e to the 5t minus 10 sine of 2t. So that's the same thing as taking the 4 times the Laplace of e to the 5t. So we're just pulling that multiple of 4 out. Same thing with the 10. We could factor that guy out. All of this works because of our rules of exponents. We found this guy before. That was 1 over s minus 5. And this guy we just found, that was 2 over 4 plus s squared. I'm just going to clean it up a little bit. And we could get a common denominator if we wanted to. I'm not going to go there. So if we want to talk about what's that restriction on S, what does S have to be bigger than? It's going to be the overlap of these. We said that when we found this Laplace, S had to be greater than 5 to force convergence for that integral. Here, S had to be greater than 0. So if we look at that overlap, think about it as a number line. Here's 0, here's 5. If S has to be greater than 0 for that sine one, and S has to be greater than 5 for the e to the 5t one, then the overlap of those would be S has to be greater than 5. You have to go with that overlap, which is the intersection of those two. So you can see how this guy's working. Let's do another one. So we could do some rewrites here. We could rewrite this as 20 times the Laplace of e to the negative 3t. We found that one. Then we could rewrite the second one as 7 Laplace of t. And then this last one, we could think about it as negative 9 Laplace of 1. The Laplace of e to the negative 3t was 1 over s plus 3. The Laplace of t was 1 over s squared. And the Laplace of 1 was 1 over s. So we have 20 over s plus 3 plus 7 over s squared minus 9 over s. So now let's think about that restriction on s. To force convergence here, we said s had to be greater than negative 3. To force convergence here, we said s had to be greater than 0. And to force convergence here, s had to be greater than 0. So if you think about that number line again, here's a negative 3 and here's 0. To force convergence of that e to the negative 3t, we said that we had to be bigger than negative 3. To force convergence on t and 1, we had to be bigger than 1. Bigger than 0. So that overlap is actually here. So s has to be bigger than 0 for this guy. So all of that works because of those properties of integrals. So let's talk about some of those basic rules. And all of these can be derived from that definition that we've been dealing with. The Laplace of f of t equals the integral from 0 to infinity e to the negative st times f of t dt. So this one we proved. That was one of the first examples we did. That was actually the first example we did. We did one here. When we found the Laplace of t, that was t to the first. So we could substitute 1 in for that n, and it would be 1 factorial over s to the 1 plus 1. 1 factorial is 1. So this would be 1 over s squared. And that's the exact same thing we got when we did everything by hand in example 2. Look at D. We found the Laplace of sine of 2t by hand using some fun Calc 2 stuff. If we were to apply this, our k is 2. So we would end up with 2 over s squared plus 4, which is the same thing we got when we did everything by hand. So you can see how these are working. There's one for cosine. The difference between sine and cosine is what's going on in that numerator. And then we've got one for sinh and cosh, which is the hyperbolic sine and cosine. And we even did a few of these. when we found the Laplace of e to the negative 3t. Our a was 3, or negative 3. So if we substitute that into this formula, it would be 1 over s minus negative 3, which would be 1 over s plus 3. So if you wanted to, you could go through and you could derive some of these for fun, or we can just use them, which is fine also. So you can see how these are definitely going to be a nice shortcut for us to do and for us to use. There's a table in your book, I'll post it in Blackboard also, that has a lot of different Laplace transforms and what the formula would be over here. And then any kind of restrictions if you need a restriction on it. So I just want to talk briefly about sufficient conditions. Not every function has a Laplace transform. We're primarily going to deal with things that do have Laplace transforms. But there are some conditions that are sufficient, but they're not necessary. However, if it satisfies the condition, then you're guaranteed to have a Laplace transform. It's really similar to, if you remember back to 172 trig, when you talked about conditions for symmetry and polar. They were sufficient but not necessary. So you may have done an example where you talked about a rose, and it may have failed every condition, but it still had symmetry. And then you may have talked about an example where it satisfied the condition, and then you could see that symmetry on the graph. This is kind of similar. It's sufficient but not necessary, which means that if you have this, then you're guaranteed to have a Laplace transform. However, if you don't, that does not mean you don't have a Laplace transform. It just means you don't know yet. You got to go through that integration process to see if you do. So, it's all based about this thing called exponential order. So if we have a function f, it's said to be of exponential order if there's constants, c, m, and t, such that this condition holds. And I'm going to rewrite this thing the other way. Let me write this as m e to the ct is greater than or equal to f of t, the absolute value of f of t. So what this is saying is that you're going to see, are there constants where this is going to happen at some point in time? That's what this t is greater than t is. And what you want to happen is you want this exponential to live above the absolute value of f of t. So that's all it's saying. That m and that c on this exponential are just performing some kind of transformation on it. So then theorem 7.1.2 says, if f is a piecewise function on 0 to infinity, and it's of exponential order, which means that there exists an exponential that if you graph this, it's going to be above the absolute value of f of t, then that means that linear transformation has to exist for that. So if we look at just a super simple one, let's say our function is f of t is equal to t. And we want to look at this exponential order thing. We want to know, is there some kind of exponential function? This is going to manipulate the exponential function. Remember, this guy could, if it's positive, and keep in mind there are restrictions on that. That m has to be positive. So this is going to vertically stretch or shrink that graph. And that c is going to horizontally stretch and shrink that graph. But are there constants where this is going to be true? Well, if we were to graph f of t is equal to t, then we're left with really just a straight line. we could keep this simple and find an exponential function and just look at e to the t. If we were to graph e to the t, it's going to look like this. So what this is saying is if you can meet this condition where some exponential function lives above, and we're looking at the absolute value here. So the absolute value of t would actually look like this. But is there a place where we pass a certain point on the t-axis, which in this case is the x-axis? Is there a certain place where an exponential function would be above that f of t function, and we want to be above it always? If that holds, then you're guaranteed to have a Laplace transform for that. So for this guy, we could just use e of t. E of t is definitely going to be greater than or equal to the absolute value of t, and that's going to always be true on the right-hand side, where t is greater than 0. In fact, it's even true just a little bit over here. So there's a place where this happens. That's going back to this. We have an exponential function that lives above that function. Exponential order is met. So we have something that's piecewise continuous on 0 to infinity. Remember, we could take the absolute value of t and rewrite it. T is going to be, absolute value of t is equal to t, as long as t is greater than or equal to 0. And it's negative t as long as t is less than 0. So we're meeting the piecewise continuous. It would be piecewise continuous here. It's of exponential order because there's an exponential function that lives above it. That means the Laplace has to exist. And in this case, the Laplace of t was 1 over s squared. So then if we have something that's piecewise continuous from 0 to infinity, and it's of exponential order, and the Laplace exists, then the limit as s goes to infinity of f of s would go to 0. So if we were to take the limit of this guy, let me rewrite it this way. As s goes to infinity of the Laplace of t, just using our simple example here, that would be taking the limit as s goes to infinity of 1 over s squared, and that guy's definitely going to go to 0. So that's all those theorems are saying. So let's look at one more where we have a piecewise function. So we want to find the Laplace of this piecewise, and we've got two pieces to this. So we do have to use the definition for this. Notice this is going to be of exponential order. If we were to graph this guy from 0 to 3, we have the function 0. And then it's just this 2 from 3 on. So we could find an exponential function that would satisfy all of this. And that would live above this graph. So we could find something that would work. We would just have to manipulate that m value to get that. Okay? So then that means that we could definitely find the Laplace. And now that we want to find the Laplace,